Hello everyone, welcome to the video. Here I'll be presenting my master's thesis research on Lagrangian methods for inviscid barotropic flow, focusing on a higher order mimetic discretization on a space-time grid. Let's begin with the motivation for this work. In computational fluid mechanics, the standard approach is the Eulerian formulation, where we use a fixed mesh and watch the fluid flow through it. However, this method has known issues. It contains non-linear convective terms that can generate small-scale phenomena which, over time, can no longer be accurately represented on the mesh. This leads to a deterioration of the solution. Furthermore, these methods pose significant and persistent problems when simulating low Mach number flows. To address this, our research uses a Lagrangian formulation where the mesh is attached to the flow. This change in perspective is powerful because it naturally eliminates those problematic nonlinear convective terms. The primary drawback, however, is that this moving mesh can itself deteriorate and tangle over time. This makes a robust remeshing strategy not just an option but a necessity. This brings us to the core task of our research, which is centered on two main goals. First, our primary objective is to delay the need for remeshing as much as possible. We achieve this by fundamentally changing where the computations are performed. Instead of working with a mesh that is actively deforming and at risk of tangling, we perform all calculations in the clean, undeformed reference space. This is made possible by using the Piola-Kirchhoff stress tensor, which allows us to relate forces in the physical domain back to the original grid. This strategy directly avoids the severe mesh distortion that plagues conventional Lagrangian methods. The second goal is structure preservation. While our method significantly delays the problem, remeshing eventually becomes necessary for very large deformations, especially in the case of fluids. When that happens, it is critical that the process respects the underlying physics. This means creating a discretization of the governing equations that does not violate the physical laws like the conservation of energy and momentum that exist in the continuous system. First, let's visualize the difference between Eulerian and the Lagrangian viewpoints. On the left, we see the Eulerian perspective, where we observe the fluid as it passes through a differential control volume that is fixed in space, and on the right is the Lagrangian perspective that we adopt. Here, the control volume moves or convects with the flow. We are essentially following the same parcel of fluid as it travels, which provides a more natural frame for many physical phenomena. To further formalize the Lagrangian perspective, we introduce some key concepts. We start with a reference or undeformed configuration at time 0, which we call B. Each fluid particle is labeled by its initial position, x. The motion and deformation of the fluid over time are described by the flow map, denoted by phi I. This map takes a particle's initial position, capital X, and gives us its new position, x at time t, in the current, deformed configuration, which we call M. The entire mathematical foundation of our method is built upon a single, elegant idea from classical mechanics, the variational formulation. First, we define a Lagrangian, which is simply the kinetic energy minus the potential energy of the system. This single expression contains all the information about the system's dynamics. The integral of this Lagrangian over the duration of the motion is called the action. Finally, we invoke Hamilton's principle, which states that out of all possible paths a system could take, the one it actually follows is the one for which the action is stationary or optimized. Mathematically, this means the variation of the action, delta S, must be 0. Now we apply this principle to our specific problem. For a barotropic fluid, the Lagrangian is given by this integral over the reference domain B. It consists of a kinetic energy term, which depends on the fluid velocity phi dot, and an internal energy term, which depends on the deformation via the Jacobian determinant J. According to Hamilton's principle, we set the variation of the action to 0. Applying the calculus of variations, this leads to an integral involving the variations of the velocity and the deformation gradient. By taking the functional derivatives of the Lagrangian, we can identify key physical quantities. The derivative with respect to the velocity phi dot gives us the canonical momentum density pi. The derivative with respect to the deformation gradient delta phi gives us a term that is equivalent to the First Piola-Kirchhoff stress tensor. Substituting these expressions back into the action equation results in the weak form of the barotropic equation of motion. This is the equation that we will discretize in our work. To handle initial conditions and external pressures, we must account for non-homogeneous boundary conditions in both space and time. We do this by adding these boundary terms to the formulation. This gives us the complete weak form of our system. This equation holistically captures the fluid dynamics in the interior, the behavior or at the initial time, and the influence of external pressure at the spatial boundaries. A key concept that arises naturally from our variational formulation is the First Piola-Kirchhoff stress tensor, denoted by P. Unlike the more familiar Cauchy stress tensor, which relates forces to areas in the current, deformed configuration, the Piola-Kirchhoff tensor relates forces in the current configuration to areas in the original, undeformed configuration. For a barotropic fluid, it's given by this expression, relating it to the fluid pressure P subscript W and the deformation gradient F. So why is this tensor so important for our method? Because working with the Piola-Kirchhoff stress means that all of our computations, that is, all the derivatives and integrals, are performed on the undeformed reference configuration. This allows us to completely avoid the complications of mesh distortion, which is a common and often fatal failure point for conventional Lagrangian methods. Now that we have established the complete continuous weak formulation of our equations, the next step is to translate this system into a discrete form that a computer can solve. We achieve this by constructing a structure-preserving numerical method known as the Mimetic spectral element method. This technique draws upon powerful ideas from differential geometry and algebraic topology to faithfully translate continuous physics into a discrete system. We treat time as another dimension, creating this space-time element. The variables are then placed on the geometric entities where they naturally live. For instance, the flow map phi is located at the points. The velocity components v are on the vertical time-like edges, and the components of the deformation gradient f are on the horizontal space-like edges. Each variable is then expanded in an appropriate basis, denoted here by psi. Complementary to the primal grid is the dual grid. Here we place the dual or source variables. The momentum, Pi, lives on the dual spatial faces, while the Piola-Kirchhoff stress, P, is defined on the dual spatiotemporal faces. This careful separation of variables between primal and dual grids is fundamental to preserving the physical structure of the equations. To achieve high accuracy, we expand our degrees of freedoms using higher order polynomials. We construct these multidimensional basis functions by taking tensor products of these 1D building blocks. For variables at points, we use Lagrange basis polynomials. For variables along edges, we use edge basis polynomials. This is the spectral element part of our method. Similarly, the basis functions on the dual grid are constructed to be mathematically orthogonal to the primal ones. They are not independent, but are in fact derived from the primal basis functions through a transformation involving the mass matrix, M. This matrix acts as a discrete version of the Hodge star operator from differential geometry. After expanding all variables in their respective basis functions and substituting them into the weak form, we can assemble everything into this final discrete system of equations. While it may look complex, this matrix is a highly structured representation of the underlying physics. Let's briefly identify the key operators. The M-Rao naught inverse matrix is the inverse of the weighted mass matrix, which relates momentum to velocity through the fluid's density. The E matrices, like E sub T10, are incidence matrices that act as discrete derivative operators. The T subscript, for example, indicates that it represents the time derivative. The N transpose matrix is a trace matrix, which is the mechanism we use to apply the initial conditions by restricting the flow map to the initial time. Finally, and most importantly, the D sub pk matrix represents the spatial derivative, the pressure terms, and the Piola-Kirchhoff stresses. This matrix is nonlinear because the fluid pressure depends on the deformation, which is part of the solution we are trying to find. It's composed of other incidence matrices and pressure-weighted mass matrices. This entire system is the discrete analog of the continuous multisymplectic formulation, and it's what the computer solves to find the unknown degrees of freedom for the flow map and momentum. To validate our method, we designed a simple but illustrative test case, the oscillation of a unit square bubble of fluid. Here, we set the interior pressure to 1 Pascal and the reference density to 1.239 kilograms per meter cube. The bubble is then immersed in an environment with a lower exterior pressure of 0.85 pascals. For the discretisation in this case, we only use a single spacetime element. For example, in the videos you're about to see, n equals 5, which means we are using polynomials of degree 5, resulting in 144 number of unknowns in the system. This is a rather small system to solve, yet as you will see, it still captures the intricate flow phenomena that take place within the deforming domain very well. Importantly, the condition number of our matrix is very low as well, which means the system is very well conditioned. This first video shows the expansion case, where the external pressure is set to 0.85 pascals, which is lower than the internal pressure. In the top left, you can see the flow map. The fluid domain immediately begins to expand outwards, deforming from its initial square shape as pressure waves propagate and reflect within. Physically, we expect the bubble to expand due to this pressure imbalance and then oscillate as pressure waves reflect within the domain. The following videos will show the simulation results and, most importantly, the conservation properties of our method. In the top, middle, and right, you can see the corresponding pressure field and Mach number. The flow remains stable and subsonic throughout the simulation. However, the most important result is displayed in the bottom row. These 5 plots show the change in total energy, mass, angular momentum, and linear momentum in both the x and y directions. As you can see throughout the entire simulation, these fundamental quantities are perfectly conserved with deviations only at the level of machine precision. This is a direct consequence of the structure-preserving nature of our method. Next, we examine the compression case. Here, the external pressure is 1.15 pascals, which is higher than the internal pressure. As expected, the flow map shows the fluid domain being compressed from all sides, shrinking in volume over time. The simulation remains entirely stable despite the dynamic deformation. Once again, I want to draw your attention to the conservation plots at the bottom. Even under these completely different physical conditions, the method demonstrates the same remarkable property. Total energy, mass, and both angular and linear momentum are all conserved to machine precision. These results validate that our formulation correctly handles pressure boundary conditions and, most critically, upholds the fundamental conservation laws of physics, and also delay the need for remeshing, which were the primary goals of this research. To conclude my presentation, let's summarize the key achievements and look ahead to future work. We have successfully developed a barotropic, inviscid fluid simulation in a fully Lagrangian frame of reference. The key achievement is that this simulation is both physically robust and numerically stable. As we've seen, it precisely conserves mass, momentum, and energy, while also remaining well-conditioned and effective for challenging low Mach number regimes. This research lays a solid foundation, and there are several exciting directions for future work. The immediate goals are to enhance the solver's capabilities by extending it to multiple elements through a hybrid formulation, developing a suitable projector to allow for structure-preserving remeshing, and extending the entire setting to a full 3-dimensional framework. Looking further, we also plan to expand the physics by including viscosity into the model. A particularly promising long-term goal is to integrate this fluid solver with a structural discretization, to develop a unified and powerful method for tackling complex fluid structure interaction problems. Thank you for your attention.